Okay, hello everyone. This is a video series on showing you how to quickly prove the circle theorems, which are often used in the IGCSE math curriculum in middle school and high school, and show the real intuition why it works, which is using arcs and angles. Now, this video is going to be subdivided in a bunch of different chapters. The first one, we're going to look at how angles are proportional to arc length, and how when we measure with a protractor, we sort of look at angles. Then I'm going to prove this theorem, which helps us show that the angle of an arc from a circle center is double the angle on a circle's edge. This is going to be referenced very often, so I'm going to call this T2. It's over here. Next, I'm going to show a theorem related to the angle of a semicircle. Then I'm going to prove that equal arcs correspond to equal angles, a theorem which uses a similarity argument. So similarity means we use ratios. And finally, I'm going to show that in a cyclic quadrilateral, if you take the two opposite angles of an inscribed quadrilateral and you add them up together, it'll give you 180 degrees. So that's what I'm going to do. So arcs, or parts of the length of a circle's circumference, are very essential to angles, because when we draw angles using a protractor, we essentially sort of have to draw arcs, because we go and place it here. Say I were to draw like a random angle here. I place this here, and I want to draw 60 degrees. I would go and start from this horizontal here of 0 degrees, and make a counterclockwise rotation over to 60 degrees. And then I can just complete the angle by forming these lines. So with every arc, you always create an angle. Repeat that with me. With every arc, you always create an angle. And in this case, it's 60 degrees. I can do this again with an obtuse angle as well. Say I want to draw a 120 degree angle. Corresponds to this arc length over here. And then I draw this over here. This is 120 degrees. Boom. Done. And a quick digression. The actual form that relates this, we obviously know that this arc length is not equal to 60 centimeters, unfortunately. But they are related due to this equation, S equals R theta, where S is the arc length, R is the radius, and theta is the angle. I'm not going to deal with that, because that's not relevant too much for this. But yeah. Equal arcs correspond to angles. And now we're going to prove one of the key theorems, which is this. If I have a giant circle here, I'm going to call its center 0. And if I make an angle relative to the circle's center and across any arc, say here, call this angle B. And if I were to make another angle that shares the same arc over here, but is anywhere else along the edge of the circle, say here, then the two angles are related in the following way. A is essentially half of B, and by using algebra, we can multiply 2 on both sides, so we get that double of angle A is essentially B. And this intuitively checks out because this angle here looks a lot smaller compared to this angle here. So we know that this angle has to be bigger than this one. Okay, but that's not unfortunately a proof. That's just using a bit of intuition based on how we're looking at the drawing. The proof, unfortunately, requires a bit more work. In order to do this, we have to first construct a radius on the circle. Where? Over here. By doing this, we're able to separate this figure here into two isosceles triangles. How do I know they are isosceles triangles? For the following reason. This shape is inside a radius, so all these lengths are R. Sorry, I shouldn't use purple. I'm going to use that for a different thing. So this is R, this is R, this is R over here. And if a triangle has two lengths adjacent to each other, which are the same, by default that means it's an isosceles triangle. So we have two isosceles triangles for free. But what's the key thing about an isosceles triangle? We know that if two of the adjacent sides are the same, then two of its adjacent angles are also the same. So now I'm going to go and write a couple of new variables, two new variables. This angle here and this angle here, which I guess I will call D. I'll call this D and D. These angles are congruent. And then this angle here, which is E. And E over here. And, oh, I lied. I need to draw two additional angles here, which correspond to this. So, only letters left I have are F and G, next letters of the alphabet. And now I'm going to create a system of free equations using the following relations. The relations that the sum of angles in a triangle is 180 degrees, and that the sum of angles in a circle is 360 degrees. You do a one full rotation, that's 360 degrees, which will correspond to this part here. And now to go and write down the actual equations themselves. So we look at this triangle first. Call this T1 and T2. So T1, the sum of those triangles is D plus F equals 180, which can simplify into 2D plus F equals 180. Now we look at the relation for triangle 2. We add up all of that triangle's free angles, which will be E plus G. So E plus G. That equals 180 degrees, but E plus E is 2E. So as they're like terms. Done here. And now the sum of angles in the circle, F plus G plus B equals 360 degrees. And I guess for another matter, this angle D and this angle E, they all add up to that big angle A over here. So we also have D plus E equals A. So sorry, it's not three equations, it's four equations. Now we just need to do a bunch of simplification here. We want to get rid of these constant numbers, 180 and 360. They don't appear anywhere in this thing that we want to get in the end. So I'm going to... Yeah, this is what I'm going to do. I'm going to add these two equations together because 180 and 180 give me 360. I can therefore combine it, by adding these parts of the left-hand side of the equation together, I can state that it equals these three angles, F, G, and B, added together. So 2D plus F plus 2E plus G equals 180 plus 180, which is 360. Which therefore means it equals to this guy over here, F plus G plus B. And there are a couple of terms that we can cancel out. 2D plus 2E plus F plus G equals B plus F plus G. We have an F and G on both sides of the equation, so we can cancel that out through subtraction. We're left with 2D plus 2E equals B, and oh, well, you know, I didn't even need to bother to use this in the end because the D plus E pops up. You see I have a 2D and a 2E. I can factor out a 2 from here. And again, apologize, I'm not the best at angle work. So 2 times D plus E equals B, but we know that D plus E is essentially this angle A. So we get that 2 times D plus E equals B, But D plus E is A, so 2A equals B. Yes, this is unfortunately what it resorts to. It resorts to simplifying a system of linear equations. And this is T2. Tedious, I know, but it's very helpful because if you memorize this particular theorem, you can get the other free theorems for free just using a bunch of quick deductions. No computation required. And that I find to be a bit cool, in my personal opinion. So, wait for a second as I erase this. We're going to look at a particular case of this theorem, theorem 2, being applied to the semicircle. Because if we agree that this relation holds true, A equals 2B, or A half equals B, I might have gotten the letters wrong, I apologize in advance. But if we accept this to be the case, then we understand if I were to draw a circle here, I were to draw a center, and I draw a random diameter here, remember that a straight line's measurement is a straight line's angle measurement is always 180 degrees. The angle measurement that is the same of a semicircle, which corresponds to this part over here. This is 180 degrees. You can check it again with your protractor itself, but if that's the case, if I were to draw some angle anywhere along the edge of the circle, that's going to have to be half of 180. So this is a special case, the semicircle theorem. Is a special case of theorem 2 that we dealt with. This is angle A and this is angle B. B will essentially equal 180 divided by 2. It's A over 2 for the case where A equals 180. And that simply gives you 90 degrees. So if I have to draw any other angle along here, say like this, or this, or this, or this, as you saw in the thumbnail of my art over here, that's 90 degrees. All those angles are 90 degrees, as bizarre as that might seem. Good, we got the semicircle theorem for free. It's much faster. Then there's another theorem, theorem 3, where if I were to draw a circle, If I were to draw a circle, and I draw two angles that share the same arc, so a picture like this. I'll call this angle A, I'll call this angle B, and they all share this arc down here at the bottom. These two angles will essentially be the same, A equals B. And we can use the same argument, the first theorem that we derived, by arbitrarily defining a center, C, and then drawing a central angle arc just from here that shares the same pink arc over here. But using the fact that using this aspect of theorem 1, we know that we can always create a new angle here, which is in proportion to the other angles. So I can just call this angle C here. And since it shares the same arc, it must be in proportion with these two other angles as well. So this is angle A. I apply theorem 1. It's going to give me 2A. And that corresponds to this arbitrary angle C over here. So C equals 2A. But I can do the same thing to here, angle B. I can do angle B, apply theorem 1. And get 2B, which is also equal to this angle C. So if you want this in a ratio form, which is how you do a similarity argument, you get that, yeah, C equals 2A, C equals 2B, and I can just divide these two equations by each other. So C over C equals 2A over 2B. C's cancel out to become 1. 2's cancel out to get A over B. Cross multiply, you get A equals B. Done. And then finally, the circle quadrilateral one, which states the following. If I were to draw a circle and inscribe any kind of quadrilateral within there, call this RSTU, then the opposite angles of that quadrilateral have to add up to 180 degrees. R plus U equals 180. T plus S equals 180. Again, we use the first theorem that we solved in order to help prove this aspect over here. And how? Well, this angle over here, we're going to say it corresponds to this arc. What you have to do is you need to draw two random segments here, which will be the radius of the circle. So we define a random center here. Go and draw these radius here, which touch the opposite corners of your quadrilateral. Should call this O, just for safety. And now I can create or write additional angles A and B, and now apply theorem 1 to this. So this angle R and this angle A, both of these share this arc over here. Which means that A is double the angle measurement of R. So 2R equals A. And if I were to do that for the opposite side of the circle, using the remaining length of the circle, this here, angle B, yes, angle B is double angle U. So B equals 2U. 2U equals B. That'd be nice and symmetric on the same area. Okay, we're getting closer. But now we also know that, again, you use the fact that the whole rotation of a circle is 360 degrees. So A plus B, when you add these up, have to give you 360 degrees. This angle here and this angle there. A plus B, this equals 360 degrees. But we know from theorem 1 that it's double of those two angles here. So we can substitute these values in to get 2r plus 2u equals 360. I can factor out a 2 now. You get 2 of r plus u equals 360. Divide by 2 on both sides. I get r plus u equals 180. Which is indeed this case, this angle r and u over here. And we can repeat this argument with the other side so that we can conclude that angles s plus t have to equals 180 degrees. And then we are done. So that's it. That's the cyclic quadrilateral theorem. The fourth theorem that we ended up doing. So yes, I guess you can conclude from doing this, a really weird fact is that circles and triangles and lines, all their properties of angles are very related and close to each other. So let me draw it here. Angles circles, lines, and triangles. We take them and we essentially just mix them up with each other in some sort of arguments, and then we're able to get these four theorems for free. There's another theorem called the alternate interior angles theorem, which I will prove later on if I have the time. Otherwise, knowing some of the key theorems that we have today, I'll leave you with this little complexing art, which basically shows that all the angles in this circle are the same. And yep, if you are an art student, you can try making a whole bunch of weird drawings and confuse and troll your classmates. That's the thing with geometry. Optical illusions are unfortunately everywhere, and we can get fooled easily in cases that just baffle our ordinary intuition. Okay, so I'll leave this to the end here. Thank you everyone for listening to my video, and please consider subscribing if you want to, and I'll create new math video content. Okay, until then, take care.